Hi guys, welcome to the next lesson on DNA manipulation, tools and techniques. In this lesson, we're going to be looking at bacterial transformation, specifically the GFP gene and the pGLO plasmid. So let's find some terms. Recombinant DNA talks about DNA that's formed from organisms or formed from fragments of DNA from different organisms. So in this case, in this experiment, we have a jellyfish over here, and this jellyfish fluoresces or is a green color. We've taken or isolated the GFP gene, that just stands for green fluorescent protein. We've isolated that gene from the jellyfish, and we're now placing it into the plasmid, this plasmid over here. So we've cut the GFP gene out with restriction enzymes, and that's created sticky ends. We've also cut the plasmid with restriction enzymes, enabling us to therefore cut out a fragment with sticky ends inside the plasmid as well as on the edges of the GFP gene, enabling them to anneal or combine together. Then we'll have DNA ligase will come in and it will be able to join the two fragments together. We can see that the pGLO plasmid or the recombinant plasmid has a larger number of base pairs than the basic plasmid because we've added a GFP gene. So as I mentioned, these GFP genes and the plasmid are cut using restriction enzymes, and this just shows you what they do is they cut base pairs at specific sequences. Here are a number of restriction enzyme sites or a number of locations in which restriction enzymes can cut the plasmid. We can see that when they are cut at this section, they produce various different banding patterns on a gel electrophoresis. So here's our gel electrophoresis, here's our negative terminal, here's our positive terminal. When we run an electric current through that gel, we can see that the uncut plasmid has the largest size, because remember, large molecules will remain up the top up here if this is the negative electrode, and smaller molecules move down further if this is the positive electrode or positive terminal. We can see that when we're cut with enzymes such as NHE and SMA, they produce smaller fragments because they have a smaller differences between the recognition sites. If we run the gel too long, these bands would eventually run off the gel. So we can see that these are the smallest fragments, which if we run them too long, will run off the gel compared to others. So we need to determine how long we run it will depend on the distance in which the base pairs have traveled. So now we have transformed our plasmid. We have a recombinant plasmid. We have the GFP gene placed inside the plasmid, and we have ARAC-C, which we'll define later, and AMP-R. AMP-R refers to ampicillin resistance. That means it gives the bacteria, or gives the plasmid, resistance to the ampicillin antibiotic. This is important as it enables us to select the bacteria of our choice. So the plasmid is moved or placed into the E. coli bacteria, as shown. You don't need to understand this process, but it's called electroporation. That's where the bacteria are either electrocuted or they can also be heat shocked, which will increase the permeability of the membrane, enabling the plasmid to be uptaken, as shown here. So now we have the plasmid inside a few bacteria. Not all bacteria will have the plasmid inside them. Because they have the ampicillin resistant gene, this plasmid will produce the ampicillin resistant protein, which will mean the bacteria that have this plasmid are now resistant to the ampicillin antibiotic. When we place them in antibiotic media, it will select for only the bacteria that have the ampicillin resistant gene, or therefore the plasmid that we've transformed. So we have only the bacteria survive that are resistant to antibiotics, and they will have the GFP gene inside them as well, in this case. In the presence of arabinose is a sugar, it will actually regulate the expression of the GFP gene. So here you can see arabinose attaches or is in contact with the bacteria, it's taken up, and that will cause the protein, GFP protein, to fluoresce green. How it does that is the ARAC-C gene, which was another component of the plasmid we saw before, the ARAC-C gene is attached to the GFP gene. The GFP gene will not be transcribed and translated unless the ARAC-C gene, or its upstream promoter, respective to the GFP gene. So here we have the ARAC-C gene is the upstream promoter for the GFP gene. So in the presence of a sugar, arabinose, it will bind to the ARAC-C protein, which creates a complex, ARAC-C arabinose complex, and that will bind as a transcription factor upstream of the GFP gene. In the presence of this particular construct or this particular transcription factor, the RNA polymerase can now bind to the GFP gene, which means it can be transcribed and then translated as a GFP protein. So without the presence of arabinose, the ARAC-C protein can't bind to the ARAC-C gene, which means the GFP gene won't have RNA polymerase bind to it, and it won't be transcribed and translated. So using this system, we can see that the ARAC-C gene enables GFP gene to be transcribed, and we can select for bacteria that have the ARAC-C gene and the GFP gene because we also have an ampicillin-resistant gene. I hope this provides some insight into what we're doing into the practical. Now, there'll be 4 plates we're going to use in the practical. We're going to have plate number 1, which will be LB. So that is just bacteria. There is no transformed bacteria on this plate. The reason why we have this plate is to demonstrate and show that bacteria can grow. That's called a lawn growth. There's complete coverage of the plate to demonstrate that we are able to grow bacteria. This one here is second plate, where we have bacteria plus ampicillin. So we can show that ampicillin, or the antibiotic, is able to select for or kill the bacteria in this experiment. So effectively, these 2 plates are our controls. The third plate over here is bacteria treated with the plasmid, so they have the pGLO plasmid, whereas these ones didn't. They have the plasmid, and we can see that our bacteria can grow in the presence of a plasmid. So the addition of a plasmid does not affect the bacterial growth. The fourth plate will contain the bacteria plus ampicillin. So these bacteria have been transformed with the pGLO plasmid, and they can grow. A small number have been transformed, and they can grow in the presence of ampicillin. So we are able to select these bacteria. However, not every single bacteria will take up both the GFP gene and the ampicillin resistant gene. So these ones here contain ampicillin resistance, ampicillin antibiotic, and the plasmid inside the bacteria. They don't have the pGLO gene in them because there will not be a complete uptake of the pGLO gene into the plasmid. This plate over here, they contain bacteria which have the ampicillin resistant gene, and they also are exposed to or given arabinose, which means it will bind to the ARAC-C protein and enable the transcription and translation of the GFP gene. These are the plates you'll be constructing the practical. I hope this provides some insight into the practical.